Alright, moving on to 5.5, the definite integral. So the integrals that we've looked at in this chapter so far have been what we call indefinite integrals, and today we're going to define what the definite integral is, and you'll have a better idea of what that means when we take a look at the following definition. So first of all, a function f is said to be Riemann integrable if integral on AB if the limit if this limit exists. And remember, this is the area, or rather the net signed area, right? This is the net signed area of f. So if this limit exists, then f is said to be Riemann integrable. Well, rather, actually there are two conditions, right? So this limit has to exist, and the limit cannot depend on the xk stars chosen. Anyway, if that is the case, then we write integral, but then we put these little subscripts on it, or the subscript and the superscript, a and b. And those, you'll notice, are the endpoints of the interval up here, right? So the way we read this is we call this the integral from a to b of f of x dx. So whereas the integral without these little numbers on it, just the integral sign f of x dx, that's called an indefinite integral. This is called the definite integral, okay? And the definite integral is the same thing as the net signed area, okay? So the integral from a to b f of x dx is called the definite integral of f from a to b. The numbers a and b are called the lower and upper limits of integration, respectively. So a is the lower limit of integration, b is the upper limit of integration. So that's a very long definition, but there you go. That's what the definite integral is. So the indefinite integral that we've been looking at, we've kind of been thinking of it as an antiderivative, right? Something that undoes differentiation. This definite integral, we see now that the definite integral is tied to the net signed area, which is interesting. So you might think, like, well, what in the world does anti-differentiation have to do with finding the area, between a curve and the x-axis or whatever? And in the next section, in 5.6, we'll see the connection between those two things. But for now, let's just focus on this definition, right? So this is what the definite integral is. So what I want to do, this is a really short section, by the way. So what I want to do is just look at a few examples where we sketch sketch a region and then calculate some areas, but using this new notation. So let's get to it. Let's sketch the region. Whose area is represented by the integral then evaluate the integral geometrically. So let's do this with this example here. Okay? So we have the integral from 1 to 4 of 2 dx. Okay, so first thing we want to do is sketch the region. So the function here, right, is f of x equals 2. That's just a horizontal line, right, that goes through 1, 2. So that's this line here. And we want to integrate between 1 and 4. So 1, 2, 3, 4. that means that this is the area that we are interested in, right? Just that little rectangle right there. So that's the sketch, and then to evaluate the integral, that just means that we need to find this area. The area of a rectangle is base times height, length times width, whatever you want to call it. So this base is length 1, 2, 3 units, right? So this is 3 units, and this height is 2 units. So it's a 3 by 2 rectangle. Therefore, the area from 1 to 4 of 2 dx is going to be 3 times 2, which is 6. Okay, we don't need a constant of integration anymore, and you'll see why in a little bit more detail in the next section. But yeah, the answer here is just 6. It's 6 square units. That's the area. Okay. Let's do another one. Let's go from -1 to 2 of x plus 2 dx. So first of all, a sketch of the region. So this has a y-intercept of 2 and a slope of 1. So I can go down 1 over 1. Or I could go up 1 over 1, I suppose. But anyway, this is the line that we get. And we're looking to integrate between -1 and 2. So this is the area, right? This is the area that we're looking at for part B. To find the area of this figure, you could either recognize that it's a trapezoid and then use the trapezoid formula, which would be 1/2 times base 1 plus base 2 times height. Or you could split it. If you didn't know that that was the area of a trapezoid, that's okay. You could just split this into a rectangle and a triangle. Right? And then you can say, alright, so the integral from -1 to 2 of x plus 2 dx is going to be the area of the rectangle, which has a width of 1, 2, 3 units and a height of 1 unit, plus the area of the triangle, which has a base of 1, 2, 3 units and a height of, well, whatever this is, f of 2, right? So if f of x is x plus 2, then f of 2 is 4, and so the height would be 4. So it would be 1/2, the area of the rectangle is 1/2 times the base times the height. Okay? So that's 3 plus 6, which is 9. I'll pause here to say another way that you could find the definite integral is to use the definition that we just wrote down a second ago, right? You could say, so you weren't asked to do this in the instructions, okay? This is just for fun, for fun, right? So you could say this. You could say the integral from -1 to 2 of x plus 2 dx is the limit as n goes to infinity of the sum from k equals 1 to n of f of xk star delta x. Right? And then you could do some scratch work like we did in the previous section to figure out, well, what's delta x, right? Well, delta x is b minus a, right? 2 minus -1 over n. That's going to be 3 over n. And then you could say, well, what's xk star? Xk star, let's see, x1 star. It depends if we're using left endpoints or right endpoints. Let's use left endpoints. So using left endpoints, x1 star would be negative 1. Or sorry. No, yeah, it would be negative 1. x2 star would be negative 1 plus 3 over n, right? x3 star would be negative 1 plus 3 over n plus another 3 over n, so we'll say plus 6 over n. Maybe here I can say 0 over n. Right? Because then we get the idea that xk star is negative 1 plus, well, what did we do? Looks like we're doing 2 times that is 4, minus 1 is 3. 2 times that is 6. Well, but that doesn't work, right? We're going up by 3s. 3, 6, so it seems like we're doing 3 times something. I guess it's 3 times this minus 3, right? 3 times 1 minus 3 is 0. 3 times 2 is 6, minus 3 is 3. 3 times 3 is 9, minus 3 is 6. So that's what it is. It's 3 times the index minus 3. Anyway, so there's a xk star. Maybe another way to do it would be to actually combine the fractions or whatever. But anyway, if that's xk star, then f of xk star is going to be x plus 2. So that's negative 1 plus 3k minus 3 over n plus 2. So in other words, that would just be 3k minus 3 over n plus 1. So we could continue on here now. We could say this is the limit as n goes to infinity of the sum from k equals 1 to n of 3k minus 3 over n plus 1 times delta x, which is 3 over n. And then you could continue on, right? Should we finish it? Let's just finish it. We can take out the 3 over n. And we're left with 3k minus 3 over n plus 1, like that. Of course, the sum from k equals 1 to n of 1 is just 1 plus 1 plus 1 n times, so this is just n. Okay, this thing we can take out an n, so I'm actually going to distribute 3 over n back in at the same time. So I'm going to get, if I factor out the 1 over n, and actually I can factor out a 3 as well, right? So if I take out a 3, then this will become 9 over n squared times the sum from k equals 1 to n of k minus 1 plus, and then here if I distribute the 3 over n here, the n's will just cancel and give me a 3. Okay, goodness gracious. Well, at this point, I think we've got it. This is just the sum of the first n minus 1 integers. So it's the limit as n goes to infinity of 9 over n squared times it's going to be n minus 1 times n over 2, okay, and then plus 3. Well, anyway, what do we get? Here we're going to get n squared minus n times 9, so it's limit as n approaches infinity of n squared, or sorry, 9n squared minus 9n over 2n squared plus 3. So limit as n goes to infinity is going to be 9 halves plus 3, though. That's not 9. We should be getting 9. We should get 9. Where did I go wrong here? Minus 3. You add 2, you get plus 1. Well, I've made a mistake somewhere, but hopefully you get the point. This should come out. This should come out to be the same thing as that, right? It should equal 9 by the time all is said and done. Unless maybe I made a mistake up here. I mean, shoot, did I? F of 2 is 4. So the height. Oh, I did make a mistake up here. You see, it wasn't the complicated stuff. It was this stuff, the easy stuff. The height of this this triangle is not 4. It's actually 3. It's 4 minus 1. So it's actually 3 plus 9 halves. Ooh, see, 9 halves plus 3 if you take the limit as n goes to infinity. All right. So all of this work down here was right. It was the easy stuff that I messed up on. Well, I'm glad that I did this then. So 3 is 6 halves. 6 halves plus 9 halves would be 15 halves. So it's 15 halves is what you should get. 15 halves in both cases, right? Anyway, we weren't asked to do any of this stuff down here. We were just asked to draw the picture and then do the geometry. Anyway, let me give you one more example, and hopefully I don't botch this one. I'm not going to do the long stuff. I'm just going to do the geometry stuff that they ask us for. So we'll do integral from 0 to 1 of the square root of 1 minus x squared dx. Let's draw a picture. So you may or may not recognize this, but notice if we call this y equals square root 1 minus x squared, and then we square both sides, and then we add x squared over to the other side, we get a circle. However, the logic only flows in one direction. So if you try to go backwards, you can subtract the x squared and then take the square root. But if you take the square root, you should have a plus or minus sign on it, right? Which means that since we're only taking the positive square root, we're only getting the top half of the circle. So it's not a full circle of radius 1. It's just the semicircle. We're only interested in what happens between 0 and 1. So it's a semicircle. It looks something like that. Okay, we'll call this 1. So this is the area that we're interested in here. But it's a quarter circle, I guess. The area we're interested in is a quarter circle with radius 1. So we can find the area pretty easily, right? So the area, or maybe I'll say, okay, so the area is this integral. It's going to be pi r squared divided by 4 because it's only a quarter of the circle. Now the radius here is 1, so that's just pi over 4. So there's the area there. Okay, so that's the idea behind the definite integral, right? It's just the same thing as the net signed area that we discussed in detail in 5.4. Okay. Now here are some useful things about the definite integral that may or may not come in handy. They probably will. If your limits of integration, if your lower and upper limits are the same, well then that area is just going to be 0, right? Imagine, it's like, if the interval you're looking at starts and ends at the same place, then of course it's going to have an area of 0, right? So that's one fact. Another fact is that you can switch the limits of integration. So instead of going from a to b, you can decide to go from b to a, and they're the same except by a sign, right? So the integral from a to b of f of x is the negative integral from b to a of f of x. So that's kind of interesting as well. Just like with the indefinite integral, you can take out constants, right? You can factor them out. You can distribute definite integrals across addition and subtraction, just like you can with indefinite integrals. And then another really interesting thing is this one. So the integral from a to b of f of x dx, you can split this into two separate definite integrals by taking some point c in between a and b. Right? So integral from a to b is just integral from a to c plus integral from c to b. Right? So you can split it into two pieces, which is kind of an interesting thing. That'll probably come up later. Okay? But for now, let's take a look at this last example for this section. Like I said, this is a really short section, not really much here to discuss, which is good because I think the previous two sections this week were kind of on the long side. But let's evaluate this integral. From 0 to 1, 5 minus 3 times the square root of 1 minus x squared dx. Okay. Well, we can use the facts that we just saw a second ago, right? We can say, well, I don't necessarily know what this thing looks like. It's probably some kind of semicircle that's been shifted around and kind of stretched out in weird ways, but I don't want to have to sit around and try to figure it out. I would rather just use those facts that we just saw in that theorem a second ago. So I'm going to say, well, this is the integral from 0 to 1 of 5 dx minus the integral from 0 to 1 of 3 root 1 minus x squared dx. And in fact, actually, let me say this. In fact, I can take out the 5, 0 to 1 dx, and I can take out the 3, 0 to 1, 1 minus x squared dx. And that's really nice because I already know this one's pi over 4, right? I just did it a second ago, right? So this is just going to be 3 times pi over 4. This one I'll have to kind of figure out, I suppose. It may have been easier to think of it this way after all, but it's going to be a rectangle with height. This one is going to be a rectangle with height 1, right? So it's kind of doing this thing. But I'm only interested in what's happening between 0 and 1. So actually, I guess it's a square, right? Because the height is 1 and the width is 1. So this is just going to be 1 square unit. So this is going to be 5 times 1 minus 3 times pi over 4. So it's 5 minus 3 pi over 4. So not bad at all, okay? And I think that's all I have to say for this section. So that's that.